Okay. So we have that, and then we derive a periodic schedule. Here shows really the one that um, requires the least buffer size, I think. I just give one token to each node and fire a CD at the same time. And for 12 times, then all of them will have completed their period. Okay. Because here you can see A fired 2 periods, but in each period it has 6 firings. So 2 times 6 should be 12. Okay, for B, it has 6 firings per period, but no, it has 6 periods, but it has B 2 firings per period. So 2 times 6, that is also 12. And for C, that's 4, and for D, that's also 2 firings per period. And if you multiply them, you get all of them to fire 12 times. And since they all only consume one value, no, this is only for C, then you can all have that here. Okay. But you can give another periodic schedule, by the way, in the exam as well, as long as it's the correct one. And you also can see from here a periodic schedule, not the periodic schedule. Okay.
I think I have a question about that. Could you go to the graphic, maybe?
Yeah.
You initiated all buffers with one element. But aren't there cases where we need more than one element to even fire?
Well, where? For example? I mean, here, you can see from here, they require at most one element. So where is the case where it needs more than one element? I don't get it.
Doesn't A consume 6 elements? Or did I understand something wrong here?
No, then you understood something wrong. For A, it says that there are 6 firings in its cycle in one period. And in each firing, it consumes 1 from Z1, 0 from Z2. No, it consumes 1 from Z1, produces 0 to Z2 and 0 to and 1 to Z5. And then it changes its state. You can somehow think of it like that. And then it consumes 1 again from Z1 and produces 1 to Z2 and 0 to Z5. And then it continues on like that for 6 firings, and then it will have completed 1 period. But in each firing, it can only consume 1.
And how would it look like if it would consume more than 1 token per firing?
Then it would be 2, 3, something, 6, and you have a vector of 6. Because here it only says how many tokens are consumed and how many tokens are produced. What these tokens are doesn't matter. Okay.
Okay.
And how it is assumed, how it is produced, it doesn't matter. Here it could be a Boolean stream, okay, a stream of Booleans, like a stream of zeros and ones. Here, the gate for the first one in like the bit, then a z becomes one, and for this one, for the second one, it can just copy the bit. So it does to main function. You get me?
Yes, I get you, but your audio quality was pretty bad just now.
Deteriorating.
Yes.
Rotting away. Yeah.
Okay, thanks.
Yes, please repeat. Okay. From where should I repeat it? I have to fix the audio thing, but I don't know if it's a problem with my internet. Then I cannot fix that. The last two sentences. Okay, so here, what this means is that it takes 6 files to complete period. Or I shouldn't use period. I should use cycle because we have period here. And this period is something different. Okay, this period means 2 cycles. Okay. Here, it says that for it will fire 6 times. It fires, changes state, switches to another rule, okay? And but that the other rule also consumes all one. Okay, what that rule is not necessarily the same. So what third rule does not necessarily say what the rules. They have same reduction and assumption, but what they do can different. Okay. People are thinking they're not hearing me. Okay, God, this is a nightmare. Let me log out. Okay, let me fix that. Okay, let's try again. Hopefully it's better this time. So someone is typing. So what it says here is that A consumes value. So A has 6 firings to complete one cycle. Okay, it fires one rule, and then you can you can see it as it changes its state, okay? And then it fires the second rule, and then the third rule, and then the fourth, and the fifth, and then the sixth. Okay, and if you see close enough, you can see the first one, it consumes 1, produces 0 to Z2, and 1 to Z5. And for the third rule, it does the same. Okay, it consumes 1 value from Z1, produces 0 to Z2, and produces 1 to Z5. Okay, but they might not be the same function. Okay, so imagine this to be a Boolean stream of zeros and ones. For the first one, it can just flip it. So if it's 0, it becomes 1 here, and put it to Z5. And if it's 1, it put a 0 here to Z5. Okay. And for the third row, it can just copy that. Okay, they don't have to be the same function. Is that fine? And for the last one, it can do something else. But in this case, it cannot, because if it's a stream of zeros and ones, that's the 2 things you can do. Okay. So here, don't be confused by that. It only says the number of consumptions and the number of productions. It has nothing to do with what it does with the value. Here, don't care what it does with the value. All we care about is the buffer. They should be bounded. So how many are coming in? How many are going out? Okay, is that fine? Okay. So here I'm also writing 1 token. It's not the number 1. Okay. There is 1 token in that buffer. I don't care what that thing is. Okay. Now, maybe for this question, is the DPM bounded? Please explain your answer. So we have to find out if it is bounded for all executions. Okay. By the way, in the exam, it not be phrased like that. It will be phrased more precisely, like, is the DPM bounded for all executions? So what you computed here, that is the T invariant. Okay, if there's a positive one and you have enough initial marking, then fine. Here we have a positive one because we can set lambda to 1. And here we have to find a positive S invariant. And here is how we solve that. Okay, first you should write the matrix, the which is like that. I think that's fine, right? Anyone has a problem with that? This? No, okay. So with that, we have to find this S. Okay. Now I have some things to say on that. This S is a vector. Okay. But that vector is could be a linear combination of multiple vectors. In this case, it is itself. It's also a linear combination because we have a lambda here. And in general, that's not the case. And here it might be confusing. Okay. So maybe first a few comments on that. Okay, if you know how to do this, okay, I'm not forcing you to try anything new or anything like that. If you know how to do this, fine. Okay, just do it your own way. But I have many students coming after the exam to me saying, yeah, I thought I know how to do that. I should have really learned that, because I will give you a procedure here on how to solve that. And in previous years, students thought, okay, I know how to do it. I don't need to learn it. But after the exam, they always tell me that I should have learned that way. I mean, that's way simpler, and it's just a procedure. And after that, it will be done. And they always think that they can solve such an equation system during the exam, but it turns out that sometimes they can't for some reason. I don't know. So the stuff they think that works, maybe because of time pressure, whatever, doesn't work anymore. Okay, maybe I would just continue. So what I do here is, what is REF? So I think you have all taken linear algebra. Okay, this REF is a form called reduced or row reduced echelon form. Okay. What does that mean? So first, this echelon, I'm not sure, but I think it means staircase or something like that. So if you look at this, this looks like a staircase. Okay. And on the edge of the staircase, now you reduce this to only one. So only one can be at the edge of the staircase. And everything above one and everything below one, they should all be zeros. Okay, and you can see from here, everything above this one and below one, they're all zeros. Okay, and it has to be this echelon form, which means a staircase-like form. And as to how you get this, well, then you just, for example, here, for the first row, it's always simple. You divide by -6, right? You have minus half, and here you also have minus half. Here you have 1 at the tip edge of the staircase. And then you subtract 2 times, now it's 1 here, from the last row. And then you have 0 here. And now everything below 1 is cleared. And you can do this like recursively. And now you get this form. Okay, so far so good. Okay, once you have that form, it's more or less done. And maybe you have to note this down here. And I have written something here on top, PF, PF, PF. Okay, so what are they? So for P, that stands for pivot. Okay. Pivot. Oh. That's for P. For F, that means free. Okay. So P means pivot. It basically means the edge of the staircase. And you can see all ones here, they're P's. Everything else, they're F. Okay. And what you do is the following. Now it's PF, PF, PF written horizontally. Now you write it vertically. PF, PF. Okay, and for the p's, and you do some function here. I will tell you what it does, and that function is minus f and the identity matrix. Don't be scared by that. I will show you how that works. Okay, minus f means that that's the negation of the free parts. We put the negation of the free parts at the piece here, at the piece. So we put the free pivots here, the negation of the free parts. And then for the rest, that's the identity matrix. I will show you. Now, for P, so we have three free parts here. In the REF. Okay, first we find minus of that. Okay, what is minus of the first free part? It should be half. Note that we put that in the P. And the second one is 0. 0 minus 0 is also 0. The third one, 0. And the last row is just all zeros. We don't care about that. Okay, for the second P, it's 0, 2, 0. Because for this F, we also need the minus of it. And for this, we also need the minus of it. Then it's half minus 1, 1. Okay, then we have completed all the P parts. This is the P row. And then we're done, because for the F rows, it's just the identity matrix. I assume you know what identity matrix is. It's basically 1, 1, 1, and all zeros. Okay, and now you can see I get the null space vectors. And the final solution is the linear combination of these three vectors. Okay, so the final solution is a linear combination, which means that this one, I should take presenter, times lambda 1 plus lack of space plus this one times lambda 2 plus this one times lambda 3. Okay, and some of you have got 1, 1, 1, 1, 1, 1 here. That is, if you look carefully, that is the linear combination of all these three added together, because half plus half is 1. 1 plus 0 plus 0 is also 1. 2 plus minus 1 is 1. And here you have 1, 1. So that is a subspace, solution space. So this is a solution space. Okay, but finally, what you need is the vector. Okay, and you have to find linear combinations of them, because that means you have to find lambda 1s, lambda 2s, and lambda 3. And you have to find one of them that makes all the components positive. Okay, I can probably also reference, if you want to really know why it works like that, I think there are many informations online, but maybe I can also share you a link. That is an open course by MIT, I think, on linear algebra. But the procedure might be a bit different than what I've described here, but should be the same. Okay, I've included the link here. I hope this is understandable. So first you find let me summarize. First, you find the reduced row echelon form, okay? And you find out the pivots and the free parts. And for the free parts, you write them the minus of free parts on the pivots. And for the free parts, it's just the identity matrix, where only the diagonal is 1. And there you have the 3 independent vectors where you can where the solution is a linear combination of them. Okay, a question that understandable? Okay, first it looks strange, but if you can do this, let me state again. If you do this, if you know how to do this, please do it your own way. But please also make sure you know how to do that. Make sure, okay. But if you don't know how to do that, this is just a procedure on how to do that. Okay, maybe we can also look and check now. Find normally it would be quite obvious. For this case, look, you can take lambda 1 to be 1, lambda 2 to be 1, and lambda 3 to be 1. Okay, and since there's a negative here, you might need to increase lambda 2 to make it positive, but it's already big enough here. So the positive thing is the linear combination. Did you get what I mean? Here you can add them together somehow by eyeballing it. Yeah. In the exam also, it's quite simple to just check it. I mean, there is a procedure for that, but I don't think we need that. Okay, maybe I can also show how it's done here. For the first question, it's the same. I mean, it's here, it's way simpler. Look, here we have the reduced row echelon. Look here, I'm not even doing the S invariant, but the T invariant. So find the solution. This is the simple one. So this is the first question. You all got it right. But here it's T invariant, so it's simpler. But it works in the same way. So you have you like reduce this row reduced echelon form, which is like that. And what is now the free part? The free part is this one. Oh God. Oh God. Yeah, I was disconnected, and then I realized that I muted myself. Okay, here it's the same thing. You have this free part here. Okay, what is minus free part? Free part. That's 3, 2, 4. Okay, you have to put the free part at the pivots. And for parts here, you will then have the identity matrix. And in this case, since there is only one component, the identity matrix is 1. And then there you have it. So this will be a linear combination of this vector. It's 3241 lambda. So it works in the same way here. Okay. For this one, you can solve for that. But I think this is just, it will stay the same. It is like that. Okay, I don't really want to do that again here. And I think most groups did that correctly. And here, after removing buffer is at 6, which means that one row removed. Let me check. Yes, I think this row is removed. No. It's the transpose. So one column is removed here. 3, 1. Yeah, right. So one column is removed, and you can still use the procedure to find that. And that procedure, you get this one, and then let's do that again. So the free part is this one. This one. First, we have minus free parts at the pivots. So it's half, 0, 0. We also have minus system. We have 2 free parts. So from there, you should know that there should be 2 independent vectors in the final null space matrix. This is minus f, and then we have minus this f, 0, 2, 0. And for the free part, we have the identity matrix, 1, 1, 0, 0. And then there you have it. But this one is actually similar to the first one, because here it's half 1, 0, 0, 0. It's half 1, 0, 0, 0, 0. And here it's 0, 0, 2, 1, 0. Here it's 0, 0, 2, 1, 0. Okay, there's 1 0 less, but another vector is missing here. Okay, so
here's linear algebra, lecture 7. I've been
Max,
talking
for your
about
question,
vector
so you have
spaces and
these 2 independent vectors. It would be this one times lambda 1 plus this one times lambda 2. And you can easily see that there is no positive solution for that, because the comes way 0. Whatever lambda 1 and lambda 2 you choose, there will always be something strange. Like here it's lambda 1, or here it's minus lambda 1, and you know that they can not be positive at the same time. So there is a solution. So for your, I think I'm not sure if I remember that correctly. You said that there is no solution, but there is a solution. So it's even a solution space. It's just there's no positive solution in that, because for whatever lambda 1 and lambda 2 you choose, you cannot make the last component positive. Okay, and since you cannot make it positive, then there's no positive S invariant. Therefore, it's not bounded for all executions. Okay, this is next week's question. I don't really have much to say on that, except for how to solve this matrix. But I think now you have an idea. What questions regarding this exercise? Okay. Oh, questions regarding this chapter? I don't think it's really a chapter. I think the only hard thing here is maybe is this matrix thing. So you have to find a solution so that which is this rate factor. From that rate vector you derive a period where after that period you will return to the initial configuration. And then you know that all the buffers will be bounded. Because then the largest buffer size is then the largest number of tokens it can hold during the period. Okay. No questions? Okay. Regarding polychronous data flow networks, or regarding quads, I think it should be done with the synchronous model of computation, if I'm not mistaken. Or
yes. Exercise sheet 5 is about polychronous data flow languages.
yeah. So what is your question there, Lars?
I have a problem with the signal language, I assume. in general. We tried to do this exercise, and at the moment we have 4 different solutions for question 1, and we are pretty sure that at least 3 of them are wrong, but we cannot really say why and which are wrong. Is there any possibility of how to do we have a tool that can compute this programming language somewhere?
No, unfortunately, no. I have to say that. Not that not in our group.
Okay,
and
because
that's probably unfortunate.
Yeah, I think it's.
Then you should have this when the professor is here. That would be interesting. What?
Sorry, I didn't understand what you said.
Yeah. I said maybe you should have asked this question earlier when Professor Schneider was here, because it would be interesting to see his remarks on that.
Yeah, maybe I should have. Because that's right.
Because we don't have that yet. And so that's maybe bad for students.
Yeah, the problem is I'm not sure if I understand the slides correctly, and I don't really have feedback.
So what is the question? So what are your questions?
Yeah, it's a bit difficult to say, really.
Yeah, but to be honest, I haven't looked at that question yet, but
Okay.
I've checked it. So I haven't worked it out yet because I haven't looked at it. But from what I see, okay, this is the. Okay, this might be quite hard. This might be quite hard.
I'm actually not sure. I think it's either quite hard or really simple.
I think it's quite hard. I mean, you're starting from n until n square, but you only have these stream functions.
Yes.
Okay. I'm not sure, but I think it's quite hard. So yeah, but I think it might be doable. Yeah. It's also interesting.
Yeah. How do we interpret this? We have this integer n, which is our
Yes.
stream.
Maybe I should share the screen.
Oh yeah.
So that everyone can see.
That probably makes sense.
Yeah.
We have this stream, and in each clock cycle, I suppose, we get one element, the first element of this input stream into our process counter, and then we can use this element in whichever way we want, and at the end of this clock cycle we want the corresponding output element to this input element, I suppose. Or do we want the output stream to... I mean, the output stream and the input stream have to be connected by the same clock, I assume.
Yes.
So if we input, if we are in the first clock cycle, we get the integer n is 1, and our output should also be 1 then.
Right. Because that's what's written here.
Yes.
If you get 2, then you get 2, and then you get box, then you should output 3, and you get box again, you should output 4.
Yeah.
And you get 0 again, you should output 0.
Okay, but in theory, this input stream could be infinitely long.
Yes.
And we can't say if it is infinitely long or not, because we only always get one element of it.
But that's not really a problem if it's infinitely long, because here I think the assumption is that there are exactly n square minus n number of boxes.
Yes, that's also my assumption, but...
So that's not a problem if it's infinitely long, because once you have 2 here, you know that there will be 2 boxes here. You have 3 here, you will know that there will be 6 boxes here. That is always finite.
Yes, but some people of my group weren't sure if they could count boxes or not. And this was my argument to say, no, it shouldn't be possible to count boxes because the stream could be infinitely long. So
but
now
why do you need to count boxes when you have 2 here?
We don't, but he wasn't sure if we could.
Okay. Yeah, but
yeah.
But I think this question should be quite hard, actually, because it might consist of fixed point computation. where you have defined a stream in terms of itself. You know what I mean? So you have z equals to z, a function on z. And then what z means is a fixed point of that function.
Yeah, I'm not 100% sure if I understood this. What you said right now.
Maybe my suggestion is to look at the DPN, because you have that already. You know how to do that. And this signal process, it's just also DPN with special nodes.
Yeah.
And maybe you can find a way to map your solution with a DPN to this signal process. Maybe. Let's see.
Yeah, I also have a question about local variables in this process counter, because we have this example with the watchdog, and they use local variables at some point.
Yes.
So local variables persist beyond clock cycles until they are updated, I suppose.
Right. So you can have local variables here. For local variable, it just means a local stream, if you would say. The local stream viewed by a local buffer. I could maybe say it that way.
Yes, and I could just assign it one variable and make sure that this stream only contains this variable, and then I could just basically have this variable somewhere stored.
Yeah.
Okay.
So my suggestion is so local variables, they are of course visible inside the process. That's for sure. But they're no longer visible after outside the process.
Yes.
So if that's your question.
No. My question was if they persist between clock cycles. So if I
well, it's a stream. It's a stream. It does not. It of course persist between clock cycles. Or maybe I didn't get your question.
Are all variables always streams in this programming language?
Yes. You see, N is a stream. O is also a stream. And if you want Z, it is also a stream.
Okay, and
let me. That's why I said fixed point computation, because then you will define like a stream in terms of itself. Then you have also defined a stream, because what the meaning of that fixed point of that equation is the fixed point of that stream, and then maybe you can do something there. You see what I mean?
Yes. I think now I see what you mean. We have to define these local variables as fixed points of the input stream somehow.
Yeah.
Okay. Yeah. But
I think that I can probably say for sure that this question is very difficult. I'm not 100% sure, but let's see. But if you cannot find the solution, maybe don't try too hard on that. I mean, you should try, but if it's you have no clue how it works, but you have the whole Christmas holiday to think about that.
Yeah. Nothing else to do anyways.
Yeah.
Yeah, I think I got it now. I think I know how to solve it. Thanks.
Yeah. And by the way, the first exercise after the Christmas holiday. That would be when? I think the holiday is until if I'm not mistaken, is it the 7th? I'm not sure. Hello, can you hear me? Okay. So semester dates. Let me have a look. So for this year, it says until the 2nd of January. So from December the 21st until the 2nd of January, which means that we will not have the exercise on New Year's Day. Okay, fair. So the next exercise will be on the 8th. Okay, 8th of January. Good. So any other questions? By the way, you can check the video that I shared where if you're unsure about what I said or you need me to repeat, just send me a mail or maybe ask next time in the next exercise and maybe I can repeat the procedure. Okay, because it is a bit tricky. Okay. So questions? What about the others? Okay. Then I assume that there are more questions. So if so, then that would be the last exercise session for this year. So I then wish you a Merry Christmas and a Happy New Year. Please take care of yourself because I think um, gatherings, especially family gatherings, it's quite. It's one of the main um, means of infection. Yeah, but the best Christmas ever. Okay. So then see you next year. If you have the questions, you can don't hesitate to send me a mail, even during the holiday. Yeah, I will reply to that. Okay. Then we'll see each other next year. Okay. Yeah. Goodbye, everyone. Take care.
You are currently the only person in this conference.